Level up your listening with Bose Quiet Comfort Ultra earbuds and headphones with immersive sound and world-class noise cancellation for a not-so-silent night. Visit Bose.com/Spotify to shop sound that's more than a present.
Hello, Saver. Whether you're saving for that trip to the tropics or saving for an emergency, now is the time to take advantage of Wells Fargo's savings options. Wells Fargo offers savings accounts that can help you save towards your goals. So, what are you saving for? Visit a Wells Fargo branch or wellsfargo.com/save to open a savings account today.
Wells Fargo Bank, N.A., member FDIC.
This is SpaceTime Series 24, Episode 76, full broadcast on the 5th of July 2021. Coming up on SpaceTime, the National Intelligence UFO Report proves to be inconclusive, discovery of a new type of supernova, and searching for the hum of neutron stars. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Well, it would appear those American military UFO sightings are no closer to resolution, with the official congressional intelligence report by the Pentagon failing to provide any explanation for most of the sightings. The highly awaited report by the Office of the Director of National Intelligence was ordered after UFO sightings by military pilots and Navy warship crews became public.
Dude, there's what's going on, bro. There's a whole fleet of them. Look on the ASA. My gosh. They're all going against the wind. The wind's 120 knots from the west. Look at that thing, dude. That's not our LNS, though, is it? It's not. That is the LNS, dude. Well, if there's like... Look at that thing. It's rotating. Nickel 6-1 Tango. Roger, oh, got it! Woohoo! Roger. There's troubleshooting. Did you box moving target? No, I took an auto track. Oh, okay. Oh, my gosh, dude. Wow, look at that, man. Look at it fly.
It examined dozens of mysterious unexplained aerial phenomena, most of which were actually filmed during military training exercises. The 9-page public version of a more detailed classified report did not discuss any specific incidents, but said there was no evidence of any extraterrestrial involvement. So sorry folks, looks like flying saucers are out. You can find that report on our website. It found that just 1 out of 144 UFO sightings by US government personnel between 2004 and 2021 could be explained, and that was a large deflating weather balloon. The report found that many sightings were probably natural atmospheric phenomena, things like ice crystals, moisture, or heat fluctuations, things that could register as flying objects to cameras and sensors on aircraft or aboard ships at sea. Most of the rest were probably birds, plastic bags, or more balloons floating in the wind. Then there's glitches in optical and electronic equipment, or just tricks of light, shade, and water. The report ruled out unclassified American drones, but it couldn't rule out classified or black projects. The authors say their report simply lacks the data to indicate that unidentified aerial phenomena are part of any foreign intelligence program or indicative of any major technological advancement by any potential adversary. The chairman of the Senate Intelligence Committee, Democrat Mark Warner, says the frequency of UFO reports appears to be increasing since 2018. So, that's that. At least for now. This is SpaceTime. Still to come, discovery of a new type of supernovae and searching for the hum of neutron stars. All that and more still to come on SpaceTime. Astronomers have discovered a new third type of supernova known as an electron-capture supernova. The discovery reported in the journal Nature Astronomy confirms a prediction made 4 decades ago and could lead to new insights into the life and death of stars. It also sheds new light on the 1,000-year-old mystery of the supernova, which would eventually become known as the Crab Nebula. Supernovae are massive explosions marking the death of stars, and these cataclysmic events are bright enough to outshine their host galaxies. Historically, astronomers have classified supernovae into one of 2 main types. Firstly, there are core collapse supernovae. These occur in the explosive death of stars far more massive than the Sun. When these stars run out of the nuclear fuel that keeps them shining, the balancing act between gravity crushing a star down towards its centre and nuclear energy pushing things outwards ends, and gravity wins, causing the star to collapse catastrophically onto itself, or is that into itself? Either way, it's what astronomers call a core collapse supernova. What's left behind is either a super-dense core known as a neutron star, or an even denser object known as a black hole, where gravity is so strong nothing, not even light, can escape. The second type of supernova explosion we normally hear about are what are termed thermonuclear supernovae. These are caused by the catastrophic explosive destruction of a stellar corpse known as a white dwarf. White dwarfs are the slowly cooling exposed cores of Sun-like stars after they've stopped nuclear fusion and lost their outer envelopes. Now, if one of these white dwarfs is in a close binary system with a companion star, its gravitational pull can drag material off that companion, slowly and gradually increasing its own mass. Now, if enough mass falls onto the surface of a white dwarf, that can trigger a sudden explosion on the surface, causing the white dwarf to brighten dramatically in an event called a nova, or new star. Once the material is burnt off, the white dwarf continues to drag more material off its companion star, and the process repeats itself. However, if enough mass falls on the white dwarf to increase its overall mass to around 1.4 times that of the Sun, it'll trigger a far more massive explosion, one powerful enough to completely destroy the white dwarf, a thermonuclear supernova. It's that the merging of 2 white dwarfs of the right masses will also trigger a thermonuclear supernova event. In 1980, Kenichi Nemoto from the University of Tokyo predicted a third type of supernova, one he called an electron-capture supernova event. What keeps stars from collapsing under their own gravity is the enormous amounts of energy produced in their core through nuclear fusion. In an electron-capture supernova, as the core runs out of fuel, gravity forces electrons in the core into their atomic nuclei, causing the star to collapse in on itself. Astronomers predict an electron-capture supernova could occur if the progenitor is a super-asymptotic giant branch star around 8 to 10 solar masses, with an oxygen, neon and magnesium core pressure supported by electrons. When the core becomes dense enough, gravity forces the electrons into the neon and magnesium ions, reducing the core pressure and inducing a core collapse supernova explosion. The supernova explosion itself appears to be weaker than usual, with little radioactivity and resulting in a neutron-rich core. In March 2018, astronomers detected a supernova, now catalogued as SN 2018ZD, about 31 million light-years away in the galaxy NGC 2146. Archival images from the Hubble Space Telescope and from Spitzer showed a faint object that was likely the progenitor star before the explosion. A spectral analysis of the supernova 2 years after the explosion, using the giant 10-meter Keck telescope on Mauna Kea in Hawaii, suggests that SN 2018ZD was the first confirmed example of an electron-capture supernova. But the spectra was only one piece of the puzzle. The authors looked through all the published data on supernovae and found that while a few had some of the indications predicted for an electron-capture supernova, only SN 2018ZD had all 6. And surely it couldn't be that unique. The new discovery does, however, illuminate the mystery surrounding one of history's most famous supernovae, which was observed by Chinese and Japanese astronomers in the year 1054. It was bright enough to be seen in the daytime for 23 days, and at night for nearly 2 years after the explosion. The resulting supernova remnant, today known as the Crab Nebula, has been studied in detail for years and years. It was previously the best candidate for an electron-capture supernova. but this was uncertain, partially because the explosion happened nearly 1,000 years ago. The new results increased the confidence that the historic SN 1054 was indeed an electron-capture supernova. This is SpaceTime. Still to come, searching for the hum of neutron stars, and major setback in Iran's nuclear missile program. All that and more still to come on SpaceTime.
Wells Fargo presents one of the surest ways to grow your money. A Wells Fargo CD account, where you can earn a 5.00% annual percentage yield on an 11-month term with a minimum opening deposit of $5,000. Visit a Wells Fargo branch or wellsfargo.com/CD rates to open a CD account and start growing your savings with us.
Wells Fargo Bank, N.A., member FDIC.
Scientists believe they can detect neutron stars through the gravitational waves they generate as they spin. Gravitational waves are ripples in the fabric of space-time caused by moving mass. Until now, they've only been detected by massive collisions involving some of the densest objects in the universe, things like black holes and neutron stars. However, new research by scientists with the Australian National University's Centre for Gravitational Astrophysics, as well as the LIGO and Virgo laser interferometer gravitational wave observatories, suggests that slight irregularities on the surface of fast-spinning neutron stars, though only millimeters high, could still be enough to generate a faint hum which could be picked up by a gravitational wave observatory. If successful, it would be the first detection of a gravitational wave event that didn't involve the collision of massive objects like black holes or neutron stars. Neutron stars are the densest objects in the universe other than black holes. In fact, just a sugar cube-sized piece of neutron star material would weigh more than 100 million tons. As we mentioned earlier in the show, they're created in the explosive deaths of stars far more massive than the Sun. When these stars run out of the nuclear fuel that keeps them shining, the balancing act between gravity crushing the star down towards its center and nuclear energy pushing outwards ends, and gravity wins, causing the star to collapse in on itself in a core collapse supernova. As the mass of the entire star crashes down onto the stellar core, the immense gravitational collapse is enough to break through what's known as electron degeneracy. That's a quantum mechanical effect arising from the Pauli exclusion principle, and it prevents more than one fermion, such as an electron, from being in the same minimum energy level quantum state at the same time. Instead, it allows even further collapse, crushing the negatively charged electrons and positively charged protons together to form neutrons, hence the star's name. You can almost imagine those little quarks changing inside, can't you? Neutron stars are thought to be just a few dozen or so kilometers wide, with masses containing between 1.4 and somewhere around 2.2 to 2.4 times that of the Sun. Scientists don't really know much about them. They're hypothesized to be composed of maybe a quark-gluon plasma core surrounded by a neutron-proton Fermi fluid and electron Fermi gas, all encased in a rigid outer shell composed of ions and electrons, and a fluid inner crust of electrons, neutrons, and atomic nuclei. The magnetic poles of neutron stars generate powerful energy beams, which are thought to emanate from near their surface. Now, if a rotating neutron star's spin axis isn't lined up precisely with its magnetic poles, the star produces an energy beam which will sweep across the cosmos like a lighthouse beacon, and that neutron star is then referred to as a pulsar. Neutron stars with unusually strong magnetic fields are called magnetars, and they could be the source of fast radio bursts. When they collide, neutron stars send incredible bursts of gravitational waves across the universe. In contrast, the gentle hum of a spinning neutron star would be very faint, almost impossible to detect. The new research targets young recently formed neutron stars, which haven't yet compacted into a perfect sphere, and so retain some slight deformities, which should emit a stronger stream of gravitational waves. As these searches become more and more sensitive, they're providing more and more details about the possible shape and composition of neutron stars. For example, are they the roundest objects in the universe? Being able to detect the signature hum could allow scientists to peer deep into the heart of neutron stars, unlocking their secrets. Osgrav Chief Investigator Professor Susan Scott from the ARC Centre of Excellence for Gravitational Wave Discovery at the Australian National University says astronomers are still trying to understand neutron stars, what they're made of, and how many different types there are. She says searching for their gravitational waves will allow science to probe nuclear matter states that simply can't be produced in laboratories on Earth.
We want to go after neutron stars because they're one of the most unexplained stars in the universe. They're the densest stars, and we can hope to probe a form of matter that we just can't probe either on Earth in laboratories or in any other systems. So how are we going to do it? Well, one of the ways we want to do it is with gravitational waves, because if there was some kind of asymmetry in a neutron star, then that asymmetry, as the star rotates, would produce continuous stream of gravitational waves, albeit very, very weak ones. And the way we imagine that these asymmetries could be produced are, for example, by the incredibly strong magnetic fields that neutron stars have. They're like 1 million billion times the strength of the magnetic field on Earth. And for instance, if they're in a binary system, then the magnetic field of the neutron star can channel matter that it steals from the companion to its magnetic poles, creating a kind of mini mountain at each pole. And these mini mountains, because of the incredible density of the neutron star, are sufficient to cause enough of an asymmetry for us to have a crack at detecting the continuous waves from them.
Now, these can only be a few millimetres high. They're incredibly small, but I guess that's all it takes.
That's right. Because of the phenomenal density in neutron stars, a small mountain even, and we don't know exactly the size yet, but maybe a few millimetres or up to centimetres would be enough if we can get enough data of that particular star to eventually detect a gravitational wave stream caused by that little mini mountain.
So the idea is you're going to start listening out for this background hum, I guess, because it will be happening all the time, wouldn't it? Because there are lots of neutron stars and they're constantly spinning, and some of them are going to be spinning in a way that points their signal towards the Earth.
That's right. And of course, with gravitational waves, we can detect them. They're given out sort of in a reasonably even fashion, and then we can detect those in any case. And in fact, we go after neutron stars that we don't know about. So we do blind searches of the sky for neutron stars that we don't yet know exist. In fact, we believe that most of the neutron star population is not observable by electromagnetic means. So that means we've only seen, quite a small fraction of neutron stars that we believe are out there. And so gravitational waves are a very powerful tool to unlock that population, because as long as they have some kind of asymmetry, then we can go after the continuous waves which that asymmetry produces.
What would it sound like? It wouldn't be the chirp, I guess.
No, it'd be like a hum, if anything. And of course, the difficulty here is that the strength of these waves is like several orders of magnitude weaker than we get from our collisions of black holes and neutron stars, which are massive events, and waves are much stronger. So obviously, we haven't detected this background hum of gravitational waves from the neutron stars in the universe as yet. But we're inching closer and closer, and as we go, we're putting further constraints on the amount of gravitational wave emission that a neutron star can have, and also on its shape, its ellipticity.
This is really fine physics you're moving into here. How do you tell the difference between a hum and just the normal quantum fluctuations of matter popping into and out of existence?
Well, we have models of the stochastic background of gravitational waves as well, and that's another target that we're going after. So we have different ways of searching for these different types of, background signals, if you like. I mean, the neutron star ones we resolve in the sense that we have directed searches for, say, supernova remnants that we hope to establish a signal from a newly born neutron star that has a kind of asymmetry frozen into it. So we do go after particular targets as well. But as I said before, we also go after we have blind searches for particular neutron stars throughout the universe that we haven't observed just yet.
So there are set profiles you sort of think this is what it should be like, so let's look for this?
That's right, yes. We have certain search methods which use templates, and we look and cover the whole sky effectively. We need to search particular frequency and what we call spin down, which is the rate at which the spin of the neutron star is slowing. We need to put those into our templates to capture the possible behaviour of any given neutron stars that are out there.
Sounds to me like you'd probably be able to pick up the glitch in the neutron star as well, if it were to glitch and quake.
Yes, and that is something that we do go after, because a glitch is something that's going to tell us a lot about the makeup of a neutron star, how the superfluid interior interacts with the crust, the hard sort of crust of the neutron star, and the immense build-up of strain and the very strong magnetic field. This is eventually going to cause things to happen, little quakes on the star, and cause glitches. And by observing these in both electromagnetic and gravitational wave emission, it's going to tell us a lot more about the makeup of these neutron stars.
And that's really the thing, isn't it? We know so little. We sort of know where they come from. We know how neutron stars are made. But what we don't understand is what they actually form into, what the structure of a neutron star is, what happens with quarks at those sort of pressures and temperatures.
Yes, that's right. Well, this is all about us finding out about the equation of state of neutron stars, the relationship between the energy, pressure and temperature within those stars. And that will tell us a lot of information about what's possible at these very extreme states of matter, and tell us about the strong force. And we need to understand a lot more about their composition to unlock many of these big questions that we still have.
Do you think there's a strong defining line between where a neutron star ends and where a black hole begins, like there is with the Chandrasekhar limit, for example, between a normal star and a neutron star? Or do you think it's more fuzzy than that?
Well, it is a little bit fuzzy. I think what's going to become clearer with time is that there's a defined mass range for neutron stars, and that we're really trying to probe with our gravitational wave observations, and we are doing that. We're finding some over 2 solar masses. I think what's a lot more fuzzy is what masses of black holes are going to be permissible, in that we have observations of black holes down to about 5 solar masses, but we're starting to find things with our gravitational wave observations using, LIGO and Virgo, which are putting objects in this strange range between 2 and 5 solar masses. And of course, there are ideas about producing black holes with much smaller masses, sort of primordial black holes and things like that. But this is still something very much to be explored. So I think the actual mass range of black holes is a lot more fuzzy, as you say, than eventually what's going to be the case for neutron stars.
It's a fascinating area, isn't it? The more we learn, the more we realise we don't know.
That's exactly right. And at the moment, in astronomy generally, it's a time of explosion, in that we are opening up possibilities to answer so many questions that have been very long-standing. The detection of gravitational waves just in the last 5 or 6 years, that's opened a whole new window. But there are also other incredible astronomy experiments out there studying neutron stars and other phenomena that we want to know a lot more about, like dark matter and dark energy and so on.
And how they're all interconnected, because that's still not covered in standard cosmology.
That's right. And that's another very open question that a lot of work is going on at the moment, and things like how rapidly is the universe expanding and things like that. But we are really making progress on a lot of these fronts. And so I think it's one of the most exciting periods in astronomy in modern times.
That's Professor Susan Scott from the Australian Research Council's Centre of Excellence for Gravitational Wave Discovery at the Australian National University. And this is SpaceTime. Still to come, a major setback for Iran's nuclear missile program, and later in the science report, confirmation of a link between mRNA vaccines and rare instances of heart inflammation. All that and more still to come on SpaceTime.
Wells Fargo presents one of the surest ways to grow your money. A Wells Fargo CD account, where you can earn a 5.00% annual percentage yield on an 11-month term with a minimum opening deposit of $5,000. Visit a Wells Fargo branch or wellsfargo.com/CD rates to open a CD account and start growing your savings with us.
Wells Fargo Bank, N.A., member FDIC.
New satellite imagery suggests Iran's preparing for another missile test following a launch failure back on June the 12th. The June 12th launch from the Imam Khomeini Missile Test Center in Semnan province was detected by US Space Command satellites. Pentagon spokesperson Lieutenant Colonel Uriah Orlan says US Space Command doesn't yet know why the launch was unsuccessful or at what stage the missile failed. Satellite images taken by Planet Labs on the 19th and 20th of June show new fuel tanks and support vehicles appearing to be ready for another missile launch attempt. The top-secret Khomeini launch site is located 320 kilometers east of Tehran. The failed launch attempt was the fourth consecutive failure of the Simor ballistic missile. The Pentagon views the Simor as a key element in the Islamic Republic's efforts to build a long-range nuclear-capable ballistic missile. Tehran's announced 3 so-called space launches this year using its Simor launch vehicle. With so many scientists and engineers defecting from Tehran, the West is learning more and more about Iran's missile program every day. The Simor, meaning Phoenix in Persian, is based on the earlier Safir or ambassador missile. Also known as the Zafir 2, the Simor is 26.5 meters tall with a launch mass of 87 tons. It uses a 2.4-meter diameter North Korean Taepyeong-2 ballistic missile as its first stage. This combines 4 synchronized Soviet Union-era Scud SS-1, Egyptian Scud-B or Chinese Scud-C missile rocket motors fed by 4 separate turbopumps, delivering around 82,000 pounds of thrust. These are supported by a set of 4 vernier engines sharing a single turbopump, which are used for attitude control and provide an additional 31,000 pounds of thrust. The North Korean Hwasong-7 or Nodong-1 missile is used as the Simor's second stage. It has a diameter of 1.5 meters and uses 4 converted Soviet Union R-27 ballistic missile vernier engines, producing 15,000 pounds of thrust, or locally built engines based on Egyptian Scud-B or Chinese Scud-C rocket motor parts. Both the first and second stage engines are powered by unsymmetrical dimethylhydrazine fuel and nitrogen tetroxide oxidizer. Tehran also uses the same Nodong-1 missile for its Shahab-3 medium-range ballistic missile, which is designed to hit targets in Eastern Europe, Israel and Egypt, and which can be fitted with either a single 1,200-kilogram conventional or theoretically nuclear warhead, or alternatively a cluster of 5 multiple independently targeted warheads or MIRVs. The International Atomic Energy Agency says the Islamic Republic has also been exploring various fusing, arming and firing systems to make its missiles more capable of readily delivering nuclear warheads. Tehran and Pyongyang have been running parallel nuclear weapons delivery system programs, both under the cover of being space programs. North Korea ended its pretense of a space program as soon as its long-range intercontinental ballistic missile program was capable of carrying an atomic warhead. Iran's expected to do exactly the same thing once it achieves parity. These latest developments come after the Islamic Republic suspended inspections by the United Nations nuclear weapons inspectors at several key sites and accelerated its nuclear enrichment program, both in violation of Tehran's 2015 Vienna Nuclear Non-Proliferation Accord. The International Atomic Energy Agency, the UN's nuclear watchdog, is especially interested in 3 sites where recent undeclared nuclear activity was being undertaken, and a 4th site where a uranium metal disk designed for use in a nuclear weapon had been stored. Producing or acquiring plutonium or uranium metals or their alloys is another violation of the 2015 Vienna nuclear deal agreed to by Tehran. Meanwhile, the Islamic Republic's stockpile of enriched uranium now stands at well over 3,241 kilograms. That's more than 16 times the limit laid down under the 2015 deal. Iran's also continuing to accelerate its nuclear activities, starting up new cascades of advanced IR-5 and IR-6 centrifuges. That's allowing Tehran to dramatically increase its production rate of enriched uranium. The centrifuges enrich uranium by rapidly spinning uranium hexafluoride gas, separating out the fissile uranium-235 from the non-fissile uranium-238. Earlier this year, both German and Swedish intelligence agencies issued warnings about growing efforts by Tehran to obtain nuclear weapons technology. The German intelligence agency also warned that over 1,000 known members of the Iranian-sponsored Hezbollah terrorist group were now operating in Germany. Meanwhile, as for Tehran itself, the oil-rich nation insists its nuclear program is exclusively for peaceful power generation purposes only. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with a science report. A new study has confirmed a link between mRNA COVID-19 vaccines and rare instances of heart inflammation. The findings by the Centers for Disease Control and Prevention Advisory Committee on Immunization Practices are reported in the Journal of the American Medical Association. The first reports of myocarditis and pericarditis from mRNA vaccines emerged in Israel in January and were quickly followed by similar reports from the United States. Myocarditis is an inflammation of the heart muscle, while pericarditis is an inflammation of the tissue surrounding the heart muscle. In both cases, the condition up until now has usually been mild and responds well to a course of treatment with non-steroidal anti-inflammatories. Interestingly, most cases so far have involved males under the age of 30. The CDC's Immunization Safety Office has reported 1,226 cases of myocarditis, with 827 or 67.5% reported a week or two after the second dose of either the Moderna or Pfizer vaccine, with chest pain, shortness of breath and difficulty sleeping being the most common symptoms. Of those identified after a second dose, 563 followed the Pfizer vaccine series. In total, that's approximately 12.6 heart inflammation cases per million doses administered in the United States. Among the 1,226 patients, 484 were under the age of 29 and roughly two-thirds were male. The CDC says patients who do develop heart inflammation after the first dose of mRNA vaccine should wait until their inflammation heals before getting a second dose, and of course they should be consulting their doctors. The World Health Organization estimates more than 8 million people have been killed by the COVID-19 coronavirus, with over 4 million confirmed fatalities and over 184 million people infected since the deadly disease first spread out of Wuhan, China. A new study has found that common artificial sweeteners can cause previously healthy gut bacteria to become diseased and invade the gut wall, potentially leading to serious health issues. The findings, reported in the International Journal of Molecular Sciences, looked at the effects of some of the most widely used artificial sweeteners on two types of gut bacteria. Previous studies had shown that artificial sweeteners can change the number and type of bacteria in the gut, but this new research shows that sweeteners can also make bacteria pathogenic, and that these pathogenic bacteria can attach themselves to, invade and kill epithelial cells which line the intestinal wall. Scientists found that a concentration equivalent to just 2 cans of diet soda significantly increased the adhesion of bacteria to intestinal cells and differentially increased the formation of biofilms. A new study says dinosaurs were already in decline for at least 10 million years before the asteroid impact which caused the KT boundary mass extinction event 66 million years ago. A report in the journal Nature Communications claims paleontologists analyzed 1,600 dinosaur fossils from 6 different dinosaur families, including ankylosaurs, ceratopsians, hadrosaurs, dromaeosaurs, troodontosaurs, and tyrannosaurs. The research suggests that non-avian dinosaurs started to decline around 76 million years ago by failing to adapt to changing conditions as the global climate began cooling in the late Cretaceous. They also suggest that many species of herbivorous dinosaurs were being outcompeted by hadrosaurs, further contributing to the decline. Well, if you're listening to us from Western Canada, you probably already know that it's been hot out there. Western Canada has been undergoing record-breaking heat waves, with some of the highest temperatures ever recorded in that part of the world. The village of Linton in British Columbia has made world headlines, repeatedly breaking Canada's record for an all-time high temperature, eventually peaking at 49.6 degrees Celsius, that's 121 degrees Fahrenheit on the old scale, recorded on June the 29th. Environment Canada issued alerts for British Columbia, Alberta and parts of Saskatchewan, Manitoba, Yukon and the Northwest Territories, warning of prolonged, dangerous and historic heatwave conditions. And Canada wasn't alone, with temperatures soaring across Oregon, where Portland hit 44.4 degrees Celsius, that's 112 Fahrenheit on the old scale. And in Washington state, where Seattle hit temperatures of 40 degrees Celsius, 104 degrees Fahrenheit. The scorching heat dome was blamed on a high-pressure ridge trapping warm air in the region. Meteorologists say because of climate change, these record-setting temperatures are becoming more and more frequent. Globally, the decade to 2019 was the hottest on record, with the 5 hottest years on record all having occurred within the last 5 years. A well-known psychic has let one of the modern-day secrets of clairvoyancy out of the bag. It seems if they can, fortune tellers will Google you first before giving you a reading. Tim Mendham from Australian Skeptics says if you want to have a bit of fun and you're going to a psychic or fortune teller, don't let them know who you are beforehand.
Absolutely. Yeah, they Google you, they Facebook you, they do all sorts of things. There's a story that this came out of in the News Limited website with a suggestion that things you've got to be careful of when visiting a psychic. But this is written by a psychic, so it's interesting that one psychic dobbing in other psychics in a way. If you phone up for an appointment and you give your real name, or especially if you are recommended by an existing client of a psychic is quite possibly, certainly has the opportunity to do some internet research on you and find out your personal preferences and things that have happened in your life, etc., right? If you're going to make an appointment with a psychic, give a different name for a start, and then they'll have trouble doing that. But I was involved on a peripheral level with a case recently of a woman who was very upset and convinced that a psychic knew all about her and knew all this intimate information that she couldn't possibly have known otherwise. And this information was so-and-so and so-and-so and so-and-so. And I went onto their Facebook page and found it in about a minute. They were saying that
all the details the psychic was claiming to
all the details that the psychic had.
It was all there on the web.
It was all there on their own Facebook page. You didn't even have to go further than that. And I pointed this out. They said, how did they know, he had an interest in bikes and he died in this particular way? And I said, look, all these bikies turned up at the man's funeral, right? You think you'd have an interest in bikes. A whole range of things like that. They were so easily found. People who were talking about it and concerned had not even bothered, but the psychic would. And I would sort of suggest that if you go see a psychic and you don't want to be Googled about it, give a different name.
I would actually suggest you don't waste your money on a psychic.
If you're going for fun, it's not a big issue. You're probably paying twice the amount of money you would to go see a movie. And, and you could easily say, don't go see a Harry Potter movie because it's full of fantasy. Yeah, it's supposed to be. So see the psychics in the same way as a bit of fun, but don't take their prognostications seriously, and certainly don't trust them to say, I saw this in the spirits, when they could easily have found it on Google. Or the big issue is when one customer recommends the psychic to another person who then phones up, and the psychic often pumps the first customer for information on their friend. And that happens quite a lot. I got so-and-so. Tell them about them. What's their problem? Et cetera, et cetera, et cetera. And the friend might actually give all the information the psychic needs.
Or you could just look at them with your wand and go, Wingardium Leviosa.
You could very much do that, actually. And I think it would be just as effective.
That's Tim Mendham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies. Or by becoming a SpaceTime patron, which gives you access to triple episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.
Wells Fargo presents one of the surest ways to grow your money. A Wells Fargo CD account, where you can earn a 5.00% annual percentage yield on an 11-month term with a minimum opening deposit of $5,000. Visit a Wells Fargo branch or wellsfargo.com/CD rates to open a CD account and start growing your savings with us.
Wells Fargo Bank, N.A., member FDIC.
Wells Fargo presents one of the surest ways to grow your money. A Wells Fargo CD account, where you can earn a 5.00% annual percentage yield on an 11-month term with a minimum opening deposit of $5,000. Visit a Wells Fargo branch or wellsfargo.com/CD rates to open a CD account and start growing your savings with us.
Wells Fargo Bank, N.A., member FDIC.